Okay, in this lecture we're going to finish our section 13.5 material on the fundamental theorem of calculus. So recall that the fundamental theorem of calculus allows us to evaluate definite integrals easily as long as we can find an antiderivative of the function that we're integrating. And recall that definite integrals represent area under the graph of a function over a given interval. So a little review of that concept, or to make that concept of area under a curve a little more precise, let's say the following. If we have a function f of x, which is non-negative, then the graph of that function, y equals f of x, lies above the x-axis, and the definite integral of f of x from a to b gives the area under the curve y equals f of x and above the x-axis on the interval from a to b. So a little review here. If we are considering a non-negative function, f of x, so its graph would lie above the x-axis on some interval from a to b. The definite integral represents the area of this region which lies above the x-axis and below the curve on that interval from a to b. Now, in the event that our function f of x is negative or takes some negative values, is non-positive, rather, I should say, the graph of y equals f of x lies below the x-axis, since the values of the function are all negative, and the definite integral of the function f of x from a to b gives the negative of the area above the curve y equals f of x and below the x-axis on the interval from a to b. So to visualize this, let's suppose that we have some function y equals f of x whose values are negative, so that our curve lies below the x-axis. And then we have that function defined on some interval from a to b. So the definite integral in this case gives the negative of the area that lies below the x-axis and above the curve, which is our function. So here, in the left-hand figure where we have a non-negative function, the area of this shaded region is simply the definite integral of our function, as we've already considered. And in the second case, where our function is negative valued, the area of this shaded region is the negative of the definite integral of our function, because we were told this definite integral would give the negative of that area. So to actually find the shaded area, we would have to make that value negative. So let's use this fact to find the area of some region, maybe bounded by a curve and the x-axis, where parts of our curve lie above the x-axis and parts lie below. So in our next example, we are asked to find the area of the region that lies between the x-axis and the graph of this quadratic function, which we know is a parabola opening upward here, over the interval from 0 to 5. And we're given a hint here that we should check if this graph crosses the x-axis within the given interval. So in order to determine if this function crosses the x-axis, we would see what its intercepts are by taking the value of our function, x squared minus 3x minus 4, and setting it equal to the equation which defines the x-axis, that is y equals 0. So to solve for x, we could factor. This quadratic can be factored as x plus 1 times x minus 4 is equal to 0. So we find that x could be negative 1 or positive 4. Now we're only interested in this function over the interval from 0 to 5. So let's look at our function here. So here we were told that what our function is, which is quadratic. So we know it's shaped like an upward opening parabola. And at the value x equals 0, my corresponding y value for the function would be negative 4. So my curve will pass through this point, and we saw its x-intercepts were at negative 1 and positive 4. So generally, we have a parabola. Let me maybe use a different color here. Or well, no, I'll stick with this for now. We have this parabola opening upward, whose intercepts are shown here. So we're interested in the area bounded by this curve and the x-axis on the interval from 0 to 5. So this intercept was at 4, so we're going 1 unit past that to get to 5. So the region of interest is the region bounded by the x-axis itself, our curve, and the lines 0 and 5, vertical lines 0 and 5. So we would have two pieces to this region. The region which is below the x-axis and above our curve on the interval from 0 to 4, and then the shaded region that lies below the graph of our function and above the x-axis on the interval from 4 to 5. So to get the total area of this region, well, we need to evaluate the area of each of these little shaded regions. So for now, just to illustrate, let me use two different colors. So to get the area of this first region, where my function lies below the x-axis, we're going to take the negative of the integral from 0 to 4 of our function f of x, which is x squared minus 3x minus 4 with respect to x. And then I'm going to add to that the area of this blue shaded region, which would be given by the definite integral from 4 to 5 of our function x squared minus 3x minus 4 with respect to x. So again, that first piece we take the negative of since our function lies below the x-axis. So let's evaluate this. Evaluating an antiderivative, for each piece we have the negative of 1/3 x cubed minus 3/2 x squared minus 4x, which is then being evaluated from 0 to 4. And then we're adding, well, we've got the same function, so the antiderivative is the same. 1/3 x cubed minus 3/2 x squared minus 4x, which is then being evaluated from 4 to 5. So for our first integral, we start by substituting 4 in place of x. So we have the negative of 4 cubed, which is 64 over 3, minus, let's see, 4 squared is 16 times 3/2 would be 8 times 3 or 24. And then minus 4 times 4 would be 16. And then we subtract what we get when we substitute 0 in for x, but we see that when we substitute 0 for x, we have a value of 0. So we're subtracting nothing there. Then moving to our second integral, when we substitute x equals 5 into our antiderivative, we have 5 cubed, or 125 over 3, minus 3 halves times 5 squared, or 25, would be 75 halves, and then minus 4 times 5 is 20. So, combining like terms, it's a little tedious here, but we could use a common denominator of 6, and then this expression can be reduced down to 43 over 2. So this would be the area of that shaded region of interest. So let's look at another one. Suppose that we want to find the area of the region between the x-axis and the graph of this cubic function, y equals x cubed minus 4x, over the interval from -2 to 4. So as with our last example, let's start by determining if it crosses the x-axis by setting our function, x cubed minus 4x, just 4x, equal to 0. So to solve, we could factor out an x. We're left with x squared minus 4 is equal to 0. So either x is 0 or x squared minus 4 is equal to 0, in which case x could be positive or negative 2. So let's see if we can visualize our region, at least get a rough sketch of this graph. So we have seen that our function crosses the x-axis when x is equal to 0, when x is equal to -2, and when x is equal to +2. Now, to get sort of a rough idea of what this curve looks like, we just really need to know whether our function is positive or negative on each of these subintervals. So between -2 and 0, if I were to substitute -1 in for my function, I see that I get a positive value. So I don't know exactly what this curve looks like, but it has to pass through those two intercepts, and it's positive everywhere between -2 and 0. Now, on the next interval, from 0 to 2, we could substitute x equals 1 into the original function. We see that we have a negative value. So I don't know exactly what the curve looks like, but on this interval, it is negative, and it has to pass through these intercepts, which we've sketched. And now we're interested in the interval from -2 all the way to +4. So if we go a bit further here, well, between 2 and 4, I could use a value of x, say, equal to 3, and I find that my function would be positive. So it's going to go positive on this portion up through x equals 4. So the region that I'm interested in is the region bounded by the x-axis in this curve on the interval from -2 up through +4. So I have the shaded region shown here, at least a rough sketch. Now, in order to compute our area, well, we see there are two portions where our curve lies above the x-axis, and one part of our region where the area lies below the x-axis. So, to get the area of this region of interest, we would first take the positive area from -2, or the positive integral from -2 to 0 of our function, which was x cubed minus 4x dx. Then we would take the negative of the area below the x-axis, that is from 0 to 2, our function x cubed minus 4x dx. And then we would add the definite integral from 2 to 4 of x cubed minus 4x dx. All right. So let's see if we can evaluate this. So each function is the same, so we're going to have the same antiderivative, namely 1/4 x to the 4th minus 2x squared. On the first interval, we're evaluating from -2 to 0, then subtracting the same antiderivative, now evaluated on the interval from 0 to 2, and then adding the same antiderivative on the interval from 2 to 4. So let's see what we get. For our first integral, when we substitute 0 in for x, we have 0. And then we're subtracting what we get when we substitute the lower limit, -2, in place of x. So let's see, -2 to the 4th would be 16, divided by 4 is 4, minus 2 times -2 squared would be an 8. Then we are subtracting our next piece, so evaluating at the upper limit, x equals 2, we would have 4 minus 8, and then we subtract what we get when we substitute 0 in, but of course we see that we have 0 when we evaluated 0. So subtracting nothing, and then we add on the end, when we evaluate at 4, we would have 4 to the 4th divided by 4, which is the same as 4 cubed, or 64. Minus 2 times 4 squared is 32. And then we subtract what we get when we evaluate at 2. So we would have a 4 minus 8. So let's see what we're left with here. So altogether, we have a negative of -8. Which is 8, then we are subtracting a -8, which is the same as adding 8. Then we are adding the 64 minus 32, which is 32. And on the end, we are, again, subtracting a -8, which is the same as adding 8. So here we have 32 plus 3 times 8, which is 24. So altogether we have a value of 56 that we're left with. Okay. So let's continue. In the next part of this section, we will talk about how the definite integral can be interpreted as the total change in the value of a function. So this theorem is referred to as the total change in a function, and it says if we have a function little f, which is a non-negative continuous function on an interval from a to b, and if we can think of f as the rate of change of a function, or the derivative of some function, capital F, so that capital F is an antiderivative of little f, then the total change in the function capital F of x, as x varies over the interval from a to b, is given by the definite integral of that rate of change function, which we know from the fundamental theorem of calculus is equal to f of b minus f of a, where capital F is any antiderivative of little f. So let's look at an example of this. So here we are told an insurance company collected data on the speed of 2 cars during a 3-hour window. So a graph below, which I'll sketch in, shows the red, a few typos here, so single V, the red car, RED, car, color red, was driving at a constant 25 miles per hour throughout this period, whereas the blue car started from rest and accelerated at a constant rate of 25 miles per hour per unit time. So let's sketch our graph to illustrate this. So here we have the speed of two cars being monitored over time. So here our x-axis or horizontal axis will be time. We weren't given a specific measurement here. And then our vertical axis is velocity, or maybe just speed measured in miles per hour. So we were told that the red car was driving at a constant 25 miles per hour. So we have 25 mile per hour speed for all time. It's constant speed. And then we were told there is a blue car which started from rest. So at time 0, its value was 0. And then this car was accelerating at a constant rate of 25 miles per hour per unit time. So for every 1 unit of time that's passing, this car increases its speed by 25 miles per hour. So at time 1, its speed would be 25. At time 2, we would have 25 times 2, or 50. And at time 3, we would have 75 for our speed. So this constant acceleration by 25 miles per hour per unit time looks something like this. All right. So now that we have our graph sketched in part A, we're asked at time 1, was the red car traveling faster than, slower than, or at the same speed as the blue car? So we've already answered that actually from generating our graph. At time 1, we see that the speed of the red and blue car are the same, 25 miles per hour. So here we can say they have the same speed, namely 25 miles per hour. And then it says at time t equals 1, was the total distance traveled by the red car greater than, less than, or the same as that of the blue car? So that is the total change in the distance, total distance traveled. So in order to determine the total distance traveled, we can recall that distance, or the derivative of the distance function or position function, would represent speed. So to get the total change, referring back to our theorem, the total change in a function, or the total distance traveled, we would need the function f, which represents the rate of change of that function. The rate of change of position is what we call speed, and we have the graphs of these speed functions for these two cars. So the total distance traveled by the red car would be the integral of the function, which represents our red car's velocity, over the interval from a to b. So if we're interested in the first 1 second, we would be integrating that function over the interval from 0 to 1. So in summary, the speed or the total distance traveled by the red car would be the integral from 0 to 1 of our velocity function, or a speed function, which we were told here is a constant 25 with respect to, here we're actually using time, not x, So we might use t as our variable. And we see that we would have an antiderivative of 25t, evaluating from 0 to 1, gives us 25 times 1 minus 0, or just 25, measured in miles here, since speed was in miles per hour. And then the total distance traveled by the blue car would be the integral of the blue car's velocity function, which we were told is accelerating at a constant rate of 25 miles per hour and started from rest. We see that this is a line, so our function would be 25t, 25 for our slope, and then plus 0, since 0 was our y-intercept. So taking 25t and then integrating with respect to t over the same interval, we would have 25 over 2 t squared from 0 to 1, which gives us 25 over 2 times 1 minus 0, or 25 over 2 miles. So here the red car has traveled further. All right. Now in part B, we're supposed to repeat the questions that we did in part A, but for a time of t equals 2. So first off, which car is traveling faster? Well, at time 2, we see that the speed of the blue car is 50, whereas the speed of the red car remains a constant 25. So here we can say the blue car is faster, or traveling faster at that moment. And the total distance traveled by the red car after 2 seconds would be given by the integral from 0 to 2 of the constant 25 dt. So we have 25t for our antiderivative. Evaluating from 0 to 2, we would have 25 times 2 is 50 minus 0, so 50 miles. And the total distance traveled by the blue car would be the integral from 0 to 2, since we're considering the first 2 seconds, of 25t dt. So again, we would have 25 over 2 t squared from 0 to 2. So evaluating at t equals 2, we would have 4 times 25 halves, or 100, divided by 2, which would be 50, minus, when we evaluate at t equals 0, we have 0. So subtracting 0 from 50, we're left with 50 miles. So here, even though the blue car is moving faster at that time, over the first 2 seconds, they travel the same total distance. And then for part C, we're supposed to again answer this question, but looking at time t equals 3. So at time 3, of course, we see the speed of the blue car is 75, whereas the red car remains at 25. So again, the blue car is traveling faster. And then if we look at the total distance traveled in the first 3 seconds, we would integrate from 0 to 3 our speed function, which was 25 for the red car. So we have 25 times t, evaluated from 0 to 3, which is 75 miles. And our blue car had a speed of 25t dt, integrating from 0 to 3. We have 25 over 2 t squared from 0 to 3. So let's see what this gives us. When we evaluate at t equals 3, we have 9 times 25, which would be 225 over 2, minus when we evaluate at t equals 0, we have 0, and 225 over 2 is, well, greater than 100, so certainly greater than 75, but to be a little more precise, we have 112.5 miles. So the blue car is traveling farther. Okay. So one application of this total change in the value of a function, if we have information about the rate of change of a function, so say the speed of a car, we can calculate the total distance traveled over a time interval by making use of this definite integral. So let's look at another example. Here we are told the rate at which natural gas was consumed in billions of cubic feet per year by the industrial sector for lease and plant fuel can be approximated by this function f of x, which is 3x squared minus 14x plus 1131, where x ranges from 0 to 15, where x equals 0 is corresponding to the start of the year 2000, and then if x ranges through 15, that would range through 2015. So we want to find the total consumption to the nearest billion cubic feet between the start of 2000 and the start of 2015. So if we have this function f of x, which represents the rate at which natural gas was consumed, then we can find the total change in the consumption, or the total amount consumed, between two time points, or a span of years. In this case, from 2000 to 2015. So our consumption is evaluated as the integral from 2000, which was corresponding to x equals 0, up to 2015, which corresponded to x equals 15. Our rate of change function, which was 3x squared minus 14x plus 1131 with respect to x. So we start by finding an antiderivative. Here our antiderivative would be 1x cubed minus 7x squared plus 1131x, which is evaluated from 0 to 15. And so if we evaluate at 15, 15 cubed is 3375, minus we have a 7 times 15 squared, which is 1575, and then plus our 1131 times 15 is 16,965. And then we subtract what we get when we evaluate at x equals 0, but we see that that value is 0, so we're subtracting nothing here. So here we would have, after simplifying, 18,765, which is measured in billions of cubic feet. Okay. So let's look at our last example. Here we have a colony of bacteria which grows at the rate measured in milligrams per hour of W prime. is equal to the cubed root of 2t plus 5, where W is the weight in milligrams after t hours. And we're supposed to find the change in the weight of the colony from time 0 to 4 hours later. So again, if we're given the growth rate, so the derivative or rate of change of the weight of some bacterial colony, then we can find the total change in that function over some time interval by using our total change theorem. So here we would be looking at the integral over our time interval, in this case from time 0 to 4, of our rate of change function, which was the cubed root of 2t plus 5 dt. And then for ease of notation, recall that the cubed root of a function is the same as taking that function to the 1/3 power. So here, this is really 2t plus 5 to the 1/3. So to evaluate this integral, we see it's a composite function, so we can make use of substitution. So here, if we let u equal 2t plus 5, then the differential of u is 2 times the differential of t, dt. And we need to change, since this is a definite integral, we need to change our limits of integration from t values to u values. So starting, if we look at the lower limit of integration, if t is equal to 0, then u, which is 2t plus 5, is equal to 5. And if t is equal to 4, the upper limit of integration, then u, which is 2 times t plus 5, well, 2 times 4 is 8 plus 5 is 13. So our original integral from 0 to 4 of 2t plus 5 to the 1/3 power dt is equal to the integral from 5 to 13 in terms of u. Then we have u to the 1/3 power, and we're left with dt on the end. So looking back at our earlier work, to solve for dt in terms of du, we have dt is half of du. So my dt on the end I can replace with 1/2 of du and pull that constant 1/2 out in front of the integral. So we now have a 1/2, and the antiderivative of u to the 1/3 would be u to the 4/3, and then we divide by 4/3, which is the same as multiplying by 3/4. And this expression is then evaluated from 5 to 13. So simplifying our answer a little bit, when we multiply our two fractions, 1/2 and 3/4, we have a value of 3/8. And then we evaluate by substituting 13, the upper limit for integration, in for u. So we would have 13 to the 4/3 power. Minus, when we substitute 5 in place of u, we have 5 to the 4/3 power. We're making use of a calculator to evaluate this. We have an approximate value of 8.26 here, measured in milligrams. Okay.